afternoon session of 3 talks, each half an hour. The first one is Tyler McCormick from University of Washington. Thank you.
Okay, thanks. Let's see. Everybody hears me okay in the back? Okay, great. All right, so yeah, thanks for the opportunity to be here. I really appreciate that that chance. These talks have been great. Have been absolutely fantastic so far, so I certainly have learned a lot. So I'd like to talk today about something I'm going to call an approach that we're calling mixtures of dense pockets, and a multi-resolution approach to networks. And the reason it's called a mixture of dense pockets is because we're thinking about trying to really sort of understand, especially as we sort of have access to networks of sort of moderate and even larger size, how we really try to effectively model a combination of density and sparsity. Overall sort of sparsity that we've seen mentioned a few times, but density that's really important for understanding the sort of structure in the network, and is especially important if you're a sort of applied researcher trying to make conclusions and contribute to science using networks. Okay, so this is work with Bailey Fosdick, who's a faculty member at Colorado State, Ted, who's a graduate student at UW. So I want to start by sort of laying down some motivation with respect to a set of applied problems and sort of motivate the reason that we're going to go about this approach using a set of examples primarily from economics, but a couple from sociology and from sort of information as well. So I want to start out by thinking about informal insurance markets. And informal insurance markets are pop up sort of all over the world, but particularly in places where access to sort of credit and more formal types of insurance aren't really available. And so you can think about I'm not going to ask you to do this as a sort of thought experiment, because I don't want you to think about something negative, but were something bad to happen, say to your health or financially, what would you do? Oftentimes in many places and many of the situations we're familiar with, what we would do is we would call up the insurance company, right? If you get into a car accident, you call your insurance company and they sort of help you out. In lots of parts of the world, we don't have these sort of formal insurance mechanisms, and so people rely on each other to try to compensate in these cases. And what I'm going to talk about today are a few examples of how that happens. And so the level of structure that arise in these informal insurance networks sort of range the gamut. They start out with the sort of global structure, the sort of overall sort of potential set of people that you could connect with. There's a piece of understanding the sort of community structure, so the people that are locally around me and understanding different types and heterogeneity across communities and groups that might be sharing information or risk. And then there's the local structure, sort of understanding the behavior of particular individuals in these networks. And here, when we think about these informal insurance markets, we can think of the edges being defined a few different ways. And so this is data from Banerjee et al. So this is social networks in a village in India. If you haven't seen this data set yet, I would highly recommend that you check it out. You can download it off the internet from this person Esther Duflo's website, but if you search for Banerjee et al. 2013, this is a science paper. This data set has information from, I've actually combined these, but it's 16 different types of relationships across 75 different sort of effectively independent villages in rural India. This is a really great data set to sort of explore heterogeneity in network relations. So if you haven't seen that, I would certainly highly recommend that you take a look. But so the kinds of things that we could talk about in insurance markets have to do with everything from sort of financial transactions, right? So in the example I gave where you get into a car accident, you might need somebody to loan you money to fix your car. Sort of health type things, right? If you have a health problem, you might call your relative who's a doctor or a nurse or a health professional. And then sort of exchanges of goods and sort of general advice. And so we can think about these things as we can think about these in the networks that drive these informal insurance markets as either the sort of actual exchanges themselves, so the exchange of dollars from one person to another, or the sort of potential thereof, right? So we might be interested in exploring, for example, the relationships that you have with your family members as a set of people that you could potentially call on should you need something. So just to take these three things very, very briefly one by one. So when we think about global structure, some of the work that's been done in this area looks at what happens when you introduce new technologies. And so this is a picture that shows growth in mobile money transfers in Rwanda from 2006 to 2009. This is from a paper that I did with my collaborator Josh Blumenstock, who's at UC Berkeley in the Information School now. But so this is a case where if we really are interested in global structure in the network, one of the things that's arising is that as mobile phones become more popular, it becomes easier and easier to transfer cash in ways that aren't geographically dependent, right? And so if we're interested in the sort of role of of location in these risk-sharing and informal insurance networks, then you could imagine that a question of interest at the global scale would be, well, how does the network look different after mobile money technology becomes popular? And you can see, so this is actually an earthquake that took place in 2008. And you can see this is the sort of change in the sort of spike in the number of mobile money users. This is it's happening right after the earthquake. That's a coincidence, but the sort of point of this picture is that the number of people that are using this technology is really increasing. And so you might imagine that if an earthquake were to happen in 2009, an interesting question at the global scale would be, well, how does the network look in terms of who's sharing who's sharing money with each other in 2008 versus in 2009 after mobile technology is there? So at the community level, at the sort of middle level here, one of the things that's of interest. So this is work from Atanzio et al. From the economics field. So this is data from 70 municipalities from rural Colombia, and so they played a risk-sharing game. Basically, this is a game where you get to choose one of two options, a sort of safe option or a less safe option, and then at the end of the day, everybody's playing in teams. You get to choose your teams, and everybody pools together how much money they have. And so the question that they're asking is, across these villages, how do familiar relations differ in terms of the way people choose to play this game, right? Because at the end of the day, you're going to get real money, right? And so if you trust your family members, then maybe you want to enter into these risk-sharing relationships where you pool your assets with them. And if you don't, then maybe you don't want to do that. And so the questions here are whether we can. So this is a plot of the actual data. So these are the 70 different, or roughly 70 different networks. There's a few that were that were not usable, but the networks that were used in the paper, this is a plot of those networks. And so how do we compare the structure that exists in these communities that are effectively separate, but that exist across this spectrum? And then at the local level, this is data from a more recent paper by Banerjee, looking at the same data that I showed you in the beginning. And this is trying to identify people who are what they call gossips, or people that would be the best people to seed new types of information or share that you might want to, new types of information or technologies. And so trying to identify people who are especially central in network. And this is about local structure because it's about identifying and understanding the role that a specific person plays, in particular an individual who's likely to sort of catalyze a new technology or a new piece of information that comes into the network. And so here, this is just a picture from their paper. So this is a CDF of the number of calls received by people they've identified as gossips, by people who are elders, so a traditional person in a position of stature, and randomly selected individuals. And you can just see here that their work to identify these people and describe these people is actually identifying people who are the people that get called. There's an experimental arm here, and as soon as the experimental technology comes in, what you see is these influential people start making phone calls. Okay, so what we'd like to do is we'd like to come up with a set of models that capture this global density and local sparsity kind of phenomenon, and allow us to capture structure that exists on these three different levels: this sort of global structure, this community structure, and this more local structure. We also like to be able to selectively direct modeling effort towards complexity in the areas that are most scientifically meaningful. And so being able to sort of decompose these sorts of local and global structure means that in places where there's lots of scientifically relevant questions, we can use a more complicated model. In places where we'd like to account for dependence, but it's not a primary interest for our scientific questions, we can use a more parsimonious model. And it has nice statistical properties so that we can foster comparison across the networks. So I'll just mention briefly that there's some previous work that's been done here. Some work by Schweinberger and Hancock did a very related approach with exponential random graph models. I'll talk more about that in a minute. The next talk, if I understand correctly, we'll be talking about sort of nested models or tree-based models, so I'll skip over that. And then the latent position cluster model is something that Brendan's talked about and has come up a couple different times. Okay, so what I'd like to do is I'd like to propose a general framework, give an example, and then talk at a very high level about some of the properties that we can show and some of the properties that we'd like to have in this general framework. Okay, so let's say that we have, just defining our general framework, let's say we have a population of actors and disjoint communities. For now, we'll assume the ties are undirected for simplicity, but that can be extended. We observe a certain set of actors, which are a subset of this population. And then with respect to the community structure, I'm going to define these terms gamma as the community memberships of a particular individual. And so here, I should preface that I'm using the word community a little bit loosely. I'll talk a bit more about what that means in the next slide. But for now, the key here is that we're assuming that the network has structure such that there's these disjoint communities. Each actor belongs to one of the communities along with a certain set of other actors. We're going to assume that the size of each of the communities is bounded. And this actually turns out to be really important for a couple of reasons. The first is that, remember I said we want to put complexity in places where we think there's the most structure. And so if we imagine the sort of notion that there's some finite amount of social capital that each person has, and we'd like to expend the most of our modeling effort in actually modeling those pockets of density, it seems reasonable to believe that those pockets of density shouldn't be getting bigger and bigger as we observe more and more nodes, up to a point, right? After a point. And so what this means that even as we continue to observe more communities, the amount of modeling effort that we'll spend within a particular community is going to level off at some point. This also allows us to make connections with other literature that's related here. So this means if you think about work in spatial statistics or work in M-dependence in time series, a key here is that when we think about these complex dependent structures, it's nice to be able to sort of think about dependent structure with respect to a finite number of units, right? And so by allowing the community structure to be bounded, it allows us to make connections with those other literatures. Okay, so the general setup here is going to look something like this. So for each set of individuals n, we have a block structure that's induced by this script y. And so basically the way you want to think about it is this block structure exists here, and we're going to differentially model the ties that occur on the diagonal from the ties that occur across the diagonal. And so you can effectively think about there being some general structure, some broad structure here, and if individuals are not in the same block or community, we're going to use one type of modeling approach, and if the individuals are within the same community, we're going to use a different type of modeling approach. And again, depending on the application, we're going to selectively add or decrease complexity. So this is the general framework. So this is the way that we define the general class of models. So we're going to define a multi-resolution model as a class over Yn that has this distribution that decomposes as follows. So the first thing is we have this set. So there are k communities. We have this set here of probability distributions defining the dependence within the community. And then we have a second set of distribution that defines what happens between the communities, right? And so the key feature here of our model is that we're going to describe both the within and the between community probabilities as latent variable models, or as mixture models if you think about them in the discrete case. So here we're going to assume there's some set of parameters that exist within each community, and there's some other set of parameters that determine the behavior between communities. And so this is a sort of intentionally very general framework. And so the sort of idea here is to think about both how we can use specific examples from this framework to answer sort of concrete questions, but also to think about whether or not this sort of is this way of thinking about the dependent structure in the network, when that makes sense and what the sort of properties are from this general approach. So this generalizes the notion of local dependence that's given in the Schweinberger-Hancock paper. I mentioned that paper generalizes, that paper discusses a similar type of model, but is restricted to the case where you have exponential random graph models within the communities. And so by moving to latent variable models, we'll be able to show that the kinds of results about this general class of properties turns out to be much broader. So the key here, and this is a sort of quote from Schweinberger and Hancock, the key here is that we have dependence within subgraphs, independence between subgraphs, right? And so this is a sort of very, this is a sort of in some sense a very sort of crude way of going through and breaking apart the structure in the network to the dependence that's within subgraphs, which I'm assuming in many applied applications is going to be what's most interesting. And then accounting for the dependence that occurs across the entire network, but overall assuming that these subgraphs are roughly independent, right? And so we can think about the framework here as producing parameters that give us the questions that we're interested in. So if we go back here, you can see that within each community we have these parameters eta, And these parameters eta are going to tell us what's going on within a particular community, within a particular group, so within a particular village in the case of the data from Colombia that I showed you. And what's more, with this latent variable framework, depending on how we do estimation, we can compare the parameters across different communities. And so if we'd like to sort of compare a parameter of our latent variable model, say, for example, our latent space model, say, for example, we want to compare the mean or the intercept to the latent space model, as Brendan talked about, we're able to do that in this framework. So we have these parameters that tell us about what's going on within a particular community. It's also possible to have parameters within each of these community structures. So for example, an individual latent space that's going to tell me about the behavior of a particular individual. You could imagine a case where you relate that to a regression model, for example, to do the kind of centrality finding that I mentioned in the Banerjee paper. And then we're going to have global parameters. So you notice that this model has these theta and omega parameters that are not integrated out here. And so here, these theta and omega parameters tell me something about the entire structure of the network. So I can understand big picture structure, sort of middle of the road structure, and very, very individual nuanced structure. Sure, yeah.
Are you taking the community memberships as known here? I know in your villages it's observed.
That's right. So this is a general framework. So when we do estimation, of course, we won't always know them, right? So for now, you can assume that that the community memberships are known. But of course, when we do estimation, that's going to get a bit tricky. And I should say that this is actually one case where, if we don't have very clear community structure, it's not clear this is the right model, right? Because it seems like this is, I mean, if it looks like we have one big community, then we should probably be just investing our modeling effort here anyway, right? Okay, so this might look a little bit familiar. So I like to file this away as great minds think alike. And the great minds here, in case it's not clear, are Brendan's and Bailey's and Ted's. So this is going to look very similar to... This is so only a few people laughed, so I could have almost gotten away with it if I hadn't said anything. Oh yeah, and James, I'm sorry. I apologize. Okay, so this is very, very similar to the model that Brendan presented about an hour and a half ago. So I'm going to go through this very quickly, but I just want to give this as an example of the kind of model that would fall into this general class that we're defining. And so here you could think about the actors as grouped into blocks based on community membership. And then you could define this sort of matrix of between block ties as effectively something that looks like a stochastic block model. This is something that, this assortativity question is something that Brendan mentioned. This will be exciting to talk with Brendan about afterwards, but we did find that having some sort of assortativity restriction in our estimation, we end up doing Bayesian estimation, and we found that having some sort of assortativity restriction in our prior structure is actually really important to get good behavior or to get meaningful communities out of this. But this notion of assortativity is really important, and to sort of draw a contrast with the way I'm presenting the framework and the sort of more general way that Brendan presented this model, I think it's fair to say that in the types of applications that I'm describing, I'm sort of effectively assuming that there's some notion of assortativity, whereas I'll let Brendan speak to that, but it seems like his approach is motivated by a little bit more of a general kind of sense. Okay, so within again, looking very familiar, within each block we're going to use a latent space model. So you can think of this as having so I tried to, it's funny you mentioned that. So I pitched to Brendan before that I should get up during his talk and put a zip drive down and say, I'm going to predict exactly what you're going to do, and then have him come up and then show this. He's like, it's magic. No, it's we traced it back to the person that we've worked with in common that we think is responsible for this. So we're gonna for sending us both in slightly different ways to the same outcome. Anyway, so the notion here is to think about a latent space model within each of the communities, and then across the community structure, we'd like to have these block model parameters. And again, sort of trying again to sort of hit complementary but slightly different pieces of the emphasis than Brendan did. You notice that this is way more sort of parsimonious with respect to the ties out here, right? So you could think about, and I think there's sort of interesting questions about what do you do if you sort of think about something like the latent position cluster model, or even a latent space model. As you expand the dimensionality of the latent space, it could potentially do as well. But really, in those models, if you have a network that's overall sparse, you're estimating a distance for every sort of pair of individuals. And what I'm arguing is, in fact, that many cases, that's sort of way over parameterizing the amount of information that you have, or that is meaningful for scientific questions. Okay, so just to highlight here, if we had really been slick, we would have merged our notation. But this is a surprise for both of us, so we're learning as we go. So we have a global structure in the model here that tells us something about the way we parameterize community sizes. Sort of to Adrian's question, we have these hyperparameters that tell us about what's going on between the blocks, and another set of hyperparameters that tell us what's going on within the blocks. And you notice I've already sort of slipped into my sort of Bayesian approach here. But really, this is sort of any function of global parameters, right? So we could think of a global parameter effectively as a function of the global posterior, right? So one thing that could be really useful to have is actually not the values in the beta distribution, not the A and the B from the beta distribution, because I find those really hard to relate to sort of applied folks. But what might actually be more useful is the distribution, or some function of the distribution of these between block probabilities. That's a completely fine, that function of the posterior is a completely fine global parameter. Okay, so we have as I was mentioning, these beta k's that we can compare, the intercepts within the latent spaces that we can compare, and then local structure described by the latent positions. So I'm just going to show one very quick example, again, since this is sort of was covered a bit in the last talk, just to show that this model, so we simulated data from our model, which we're calling the block latent position model, and the latent position cluster model over here. And just to show that for simulations with holdout data, you sort of see the performance that you would expect. So when the model is simulated from ours, we sort of see, okay, great, we're doing well, both for the within block ties and the between block ties. But when it's simulated from a latent position cluster model, what you can see is that for ours, and this is, sorry, AUC on the axis here, what you can see is that for, oh yeah.
So it's the model it's simulation from is on the top.
That's correct, yeah, that's correct. And this is the...
What's fitted is on the bottom, gotcha.
Yes, sorry, that's right, I should have explained that axis. So what it's fitted from is on the y-axis. And so what we can see here is sort of what you would expect. So the stochastic block model is not trying to model between block ties, so of course or within block structure, so it of course doesn't do particularly well in that case, but it does very well in the between block ties. And what you can see here is that our model actually doesn't do as well as the latent position cluster model for modeling between block ties when we simulate from the latent position cluster model. And this is sort of exactly the behavior I would argue that you would expect, because we're really differentially saying that we're going to contribute modeling effort towards the within community ties. That's really the structure we're trying to capture, and that's sort of exactly what you see here. Okay, so let me talk a little bit about inference, and this is sort of with the spirit of, in the spirit of talking about some properties that I think are particularly important when relating these results to the sort of economists and sociologists that I work with, and also just in terms of thinking about the kinds of properties and the kinds of goals we have when we build these models. So if we think about the key piece of this model here is that I mentioned this sort of connection with these notions of independence and the sort of spatial statistics kinds of things. And if you think about the kinds of structure that we have, encoded in this model, this modular structure means that we can sort of decompose these within community parameters, and we can actually think about this notion of sort of replication of these communities over and over again, right? And so I'm implying something about a sampling process, and I'll talk about that in just a second. But this notion of getting to observe these communities multiple times, the parameters that talk about these within community blocks, and this notion of dependence within a community, effectively independence across communities, means that we have, for some of the parameters, some notion of replicates, which is something that we don't have if we think about just the global structure in the network overall. And so I'm sort of saying this in a very sort of vague way here intentionally, but if we get a bigger sample, if we get more data, we expect to get more information about these community levels and these global parameters, right? We don't necessarily have more information about how I behave, right? But we do expect to have more information about what my community's like and what the network looks like overall. And this relates to this notion of projectability. And so this notion of projectability just says that we've sort of seen it come up a few times today. It's sort of discussed in Schlesy and Rinaldo in 2013 for exponential random graph models. And so what we can see is that, so I'll just explain this here in terms of the picture. What I'd like to be able to do is I'd like to be able to marginalize over any other fraction of the graph without having the distribution of the part that I've marginalized over be affected, right? And so here it is. If I have some distribution, I can think about, if I have some distribution on the graph, I can think about that distribution as decomposable as into a part that comes from the entire distribution is decomposable into a part that comes from some subset M, and it's marginalized, or that comes from some subset of n called M. I should use different letters that are easier to say. I can break the model up into subsets, and I can reassemble the original probability distribution by assembling those marginalized subsets. And the picture here is really, I think, what's illustrative. I'd like to be able to go back and think about building up the probability distribution that encodes the entire graph by using the probability distribution for any particular subset of the graph. And you can think about this in terms of a sort of parallel to sampling, right? If I think about a sort of missing data framework or a sampling framework, I can think about sort of marginalizing over the data that I don't get to observe, right? And projectivity, as it's sort of often called in sort of other contexts, or projectability as I'm calling it here, that just means that the model is consistent under this notion of sampling. The Schweinberger and Hancock approach describes something similar, which is called domain consistency. So domain consistency means that the model is that the probability distribution of the model is preserved under marginalization over entire communities. And so from the perspective of data collection, that means that I need to be able to understand what the community structure is in the network, and I need to be able to collect the entire community in order for my probability structure to be preserved. Projectivity is a much broader notion. However, and it means that we can actually take any sort of subset of the data that we'd like, and we can marginalize over that subset of the data. Okay, and so the nice thing about sort of moving to a latent variable approach is that it means we can think of multi-resolution models, the class of models that we've defined, as projective, which is a sort of more general statement than the Schweinberger and Hancock statement. And the intuition here is that the within and between models don't depend on the size of the sample that I observe. Each of the latent variable models themselves are from a projective class of models, and then we're able to show that by assembling these collective classes of projective models in this way, we're also able to get a projective model. And so this sort of notion here that the within and between models don't depend on n is really important, right? So this is really telling me something about where the sort of dependent structure in the graph is going to be. It also means that by not allowing the between block probabilities to depend on n, it means that if I think about simulating from this model up to infinity, I'm going to get something that's asymptotically dense. And that's a feature of the model, right? And the way that works is that's saying that for any finite n, for any sort of specific sample size, I can think about a way I can certainly model a very sparse graph, an arbitrarily sparse graph for that sample size. I can estimate parameters that are very, very small. But if you think about the sort of within community ties and between community ties, as the sample size gets bigger and bigger, even if I have a finite number of ties that are coming from within my community, if I don't have something to clamp down the probability between the communities, right, as long as I have a non-zero probability of a tie between the communities, there's always going to be some probability associated with ties to just about everybody else in the network, and that's going to give me something that's asymptotically dense. And so I'm going to skip this little animation, which is probably a good thing, and just pose two questions to stop. And I think that these two questions sort of really come to the sort of forefront here when we think about when we think about what we actually want from these sorts of models, and especially as we sort of think about the kinds of results that we'd like to posit from models that have either generative models that may or may not have sort of sparsity implications in the limit, or sampling-based models or sampling-based approaches like I'm talking about now. And so I think these are sort of two questions that that seem like they should be similar, right? So this notion of growth in the way we've defined it in terms of the generative models and the exchangeability arguments that have happened in previous talks, and the sort of sampling approach that's implied by the projectivity, intuitively those two should be interchangeable, right? We should be able to go forwards and backwards. But I would sort of posit that these two questions, so from the growth perspective, what types of hypothetical populations can I generate starting from my sample? I would argue that that's a sort of subtly different question when you take that to an economist or a sociologist or to a biologist than a second question, which is what features of the population can I reasonably expect to learn about with my sample? And the reason is just sort of for two things. First is, what are the goals of my model, right? So the first question, in order to be able to simulate from a model, I have to specify a model, right? So the second question is much more, my second sort of question here is much more sort of a nod towards generalized estimating equations or the sort of model-light type approaches that we see in lots of places where we don't necessarily expect the model to be describing a population, but we do want to know that if we have a feature of the population in the model, I'd like to be able to know something about how good that's going to perform in terms of estimating a feature of the population, right? Whether the model is correct or not. And the second has to do with the sampling process, and I think this is a sort of really big open question. If you think about what happens if you have a population that's infinite and then you sample from it, what a simple random sample from that population looks like, right? Well, it's probably going to be empty. It's almost certainly going to be empty. But we see lots of data that doesn't have empty graphs, right? So if we really want to sort of think about the sampling question, we have to think about how we want to sort of account for the fact that we're sampling based on some notion of community structure or some notion of sort of understanding of structure already. And then furthermore, if we think about how growth happens, what the implications are of the different sorts of sampling mechanisms if we think about growth in the opposite direction. Okay, so I think that could go on for a long time, but I will just stop here and say thanks for listening.
So when you talk about predictivity of this class of models, are you making assumptions about these? Is it somehow conditional on the community structure, or are you sampling over the community structure? Because the communities are finite size, right?
So
which seems subtle to get.
So that's right. So this is conditional on the community structure.
Right.
Yeah. This is so when you switch to the sort of estimation question, you do have to think about that. So I'm assuming that you can get a consistent estimate of the community structure somehow. Yeah. Yeah.
Could you go back to the previous slide?
That one. Yeah.
Yeah, thanks. So I think in a sense that maybe hasn't quite been formalized. Maybe some of Peter's work gets towards that. Exchangeability is about choosing individuals in a large population at random, and so that in some sense.
Sure.
If you think about the size of the graph as indexing or determining the number of people you've sampled, that's why you get emptiness. So anyway, so I think there's been some progress on these questions, and actually I'm talking in after UI, so I'll talk about that.
Yeah.
But I think there's you can't. I don't think you can go too much further by sampling people at random from a population. It's kind of a perverse way to study a large network, especially if it's sparse.
Sure.
But there is a way around it, basically, that comes really from the Caron-Fox perspective, which is that you throw away isolated vertices in the course of sampling.
So I think that completely makes sense, but then the question becomes sort of how do we flip that on its head and think about estimation where the estimators say something about what we think the population looks like, right?
Yes,
so I think that's the...
We have built estimators as well, so I'll talk about that, and then insofar as they're perverse, we can then maybe look for different probabilistic symmetries.
Yeah. No, so I think just to sort of maybe sum up the sort of statement there, I agree. This is a sort of big question. These are sort of big questions. I think just to sort of emphasize my take on this for 10 seconds here. I mean, I really do think that this notion of course we're not going to be sampling at random from the population, right? So what I'd like to be able to think about is how I can go and explain to people who are actually collecting data how they should be sampling, in order to enable them to get estimators that have something that is as simple as the sort of types of consistency results you get about things like the mean, right, or a regression coefficient. And I think that at least my sort of understanding is that the connection there isn't quite there in my head. So if it's there in an hour, I'll be super happy, or much longer than an hour. But yeah.
Right.
Yeah.
Maybe one more quick question.
Yes.
I think the projectivity condition that you reference is very closely tied to this notion of simple random sampling, though. So if the sampling scheme was different, then that would go out the window, right? It would be much more complicated.
So which part would be? So I agree, but which part is the?
Well, I'm saying the projectivity condition, as you defined it, is defined with an implicit assumption, I believe, of this simple random sampling.
So I think it's any arbitrary set, right? So I think because we're not actually sampling, we're just marginalizing, right? And so I think
it depends on how you pick that set.
So I agree, and so I think this maybe actually comes to the point, right? So if we knew how to pick the set, right? If we knew something about the population, we knew how to pick the set, then I think we would be okay, right? But I think if we don't know what the population is, we don't know how to pick the set, then it's sort of a chasing our tail kind of thing. I think that might actually be the sort of crux of the point. Yeah.
Great. Okay, let's thank the speaker again.